All right, this is 9.1 part 2. We're still talking about sequences, which are lists of numbers, ordered lists of numbers. And another way to get a list, and by the way, we don't really like this method in algebra. Sometimes it's necessary, but we really don't like it. But it's this idea of defining something what we call recursively. So a couple of things I have to tell you about sequences and about what we're doing right now. And that is, the first thing is, if I had a number line and I called a point n, the point before and after that, they would be n plus 1. The point before would be n minus 1. That's what I call number line thinking, and I don't know what it is, but students really resist number line thinking. Maybe not on a number line, but they resist it when I talk about a list of numbers. So if I talk about a list of numbers and said there's a1, a2, a3, ... let me put a space over here, a sub n, what's the number after a sub n? Well, it's a sub n plus 1, because I'm going to the next term. And the term prior to that would be a sub n minus 1. This most likely is fairly foreign to you. In other words, you probably have never had to think this way. I mean, if I put a real number in there, the 100th term, the term before that is the 99th, the term after that, 101st, you probably understood what I said, but when we say the nth term, it's not a, we also consider it the general term. It's not a specific number. We're not saying anything about n. We're just saying something general about every term when we talk about the nth term. And in general, the nth term has a term after it that's n plus 1, and the term before that's n minus 1. All right. So if that's true, what does it mean to define a sequence recursively? Well, you have to be given two things. You have to be given a starting term, and hopefully it's a starting term. Technically speaking, you can be given any term. You can be given the 17th term. It doesn't really matter what term, but usually we say the starting term. You're given the starting term, and then you're given this relationship between what? Any term and its previous term. So you think of this as the nth term. Again, that's just a way of saying any term is equal to 4 plus its previous term. How do we implement that? Well, you just kind of get into the problem and make your list. So if the first term is 2, how do I find the second term? Well, the second term is going to be 4 plus the first term. In other words, I'm going to add 4 to this number. I'll get 6. Well, this still applies. The third term is 4 plus the previous term. So I'm just going to add 4 to this term. I'll get 10. And I just keep on going with that reasoning. Now, this is a particularly easy example. Sometimes you have to, the work is a little more complicated. I don't know, you might have to multiply the previous term by 2 and something, but if you can do it for some of these, I think you'll get the idea. So here's a good example. The fifth term is 4 plus the previous term. And how do we know the previous term? Well, we calculated it earlier. And that's the weakness of a recursively defined sequence. If I asked you to find the 100th term, you can't just say, oh, the 100th term is 4 plus the 99th term. Although that's true, what's the 99th term? Well, we don't know until we find it. But we'd also need to find the 98th term to find the 99th term. So that's why they start off giving you the first term, and recursively defined sequences kind of have to just grow from the information that we have. You can't find the 100th term without the previous one. Now contrast that with, if we knew the formula for this sequence, which I think is for n minus 2, and if you just knew the not the recursive sequence, but the general formula for the sequence, that is so much easier. I can just find the 5th term by plugging in 5. I can find the 100th term by plugging in 100. In other words, this is the type of goal that we typically seek when you have a recursive formula. They're out there, but we prefer formulas for our sequences for like I say, obvious reasons. You could find any number without having to know all the previous numbers this way. All right, so this one, more complicated formula, so finding the formula might not be possible for us, but what they do, they gave us 2 sequences, or 2 terms, the first 2, and then they told us any term is the difference, so the difference of what would this be in relation to n, the previous term, n minus 1, and then the previous term, the term before that. So let's put in some numbers here. The 5th term would be the difference of the 4th term minus the 3rd term. Yeah. This is what they mean by the nth term. This would be n minus 1, and this would be n minus 2. So the first one we have to calculate, they already gave us u sub 1 and u sub 2. To find u sub 3, do the subtraction. And we get 1. To find u sub 4, we do the subtraction, and we get negative 1. To find u sub 5, you can see how it works. Not seeing a solid pattern here yet. So the hope of getting an actual formula for that particular term, or this particular sequence, just isn't available to us. So we would just keep the recursive formula without trying to come up with the notation. All right, with another notation. In other words, this is useful if we need it to find the formulas, to find the numbers. All right, so back to the idea of non-recursive formulas, knowing the formula directly. We have something like this. So this thing here is an uppercase Greek letter sigma. Now you're not going to be drawing these by hand, but most students just kind of draw them a little more freehand than this. But the Greek letter sigma always has certain parts to it. And it's part of summation notation. And what it has is a starting value that goes on the bottom, an ending value that goes on top, and a formula. And the variables we use for some reason are I, J, and K. I, J, and K, just that area of the alphabet, seems to be the what we use. All right, so let me change this from n to 5. to make it look like a little bit more of a common type of formula. So what is it saying? K takes on all values starting with 1 and ending with 5. Start and end. Now, sigma always means you're going to add those values together. And this is the formula. What are we going to do to K? Well, we're going to cube it. So in my example with the 5 there, it's 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, or 1 plus 8 plus 27, let's see, 64, 125. I haven't worked that out, but we would work that out with a calculator, add those together. All right. So when they don't put a number up on top, they just put n up on top. Keep in mind, k is the value that changes. It takes on the values 1, 2, 3, and then up to n. Now, this is something I was just talking about. What is the previous term? What term would be right there? The term before 4 over n. Well, we don't know what n is, but we know that the term prior would be 4 over n minus 1. Just saying, you might need that sometimes. The term after it would be 4 over n plus 1. That's not so frequent that you would need that, but this one can be very, very important sometimes. So you have to see what's not there. All right. But this type of number line thinking is only required if you actually have a letter here. You know, if you have a 5, it just kind of pops out. I mean, you don't need to ask yourself what's the term above, before 5. Everybody knows that it's 4, but what's the term before n? When you have a letter, yeah, n minus 1. All right, so here they're asking us to kind of repackage a list. So what do we have here? So a couple of things we're going to need to figure out is it's obviously, we're obviously adding, so it's going to be summation. We're going to start our k at 1, and that's a little controversial, but this website always wants us to start at 1. Don't start at some other number like 2, even if you think that's better. Start at 1. I have to figure out my formula, and I have to figure out my ending value. So one thing I'll add to this is that's 8. Next will be 10, 12, 14, and then 16. So how many terms? 1, 2, 3, 4, 5, 6, 7, 8 terms. And in this case, anyhow, that also means the finishing term is 8. The final term is 8. Be careful on that. Sometimes the number of terms is not the number that goes up there, especially if you don't start at 1. But there are 8 terms. And then what's the formula? What are we doing to this number k that takes on all the numbers from 1 to 8? Well, hopefully you can see it. This is 2 times 1, 2 times 2, 2 times 3, 2 times 4, up to 2 times 8. In other words, it's 2k. So sigma k equals 1 to 2k. By the way, there's something that we're going to be doing very soon, and that is when you have a 2 or any number, you can actually bring that out front. And just leave the k behind. It's factoring out a constant. And factoring out a constant is going to be one of our tools that we're going to learn how to do in the next example. All right. So you can see how they kind of mapped it out here. They didn't do that last step. And I just want to say that this type of question is a slightly unclear because mathematics in general does not require us to start with 1. If it did require us to start with 1 in this in the sigma notation, you wouldn't have to state it here. But no, we have to start with a 1 because that's the game the author set up. And that drives everything, including the formula. You know, if I had started my formula at my sum at 2, that would have changed the formula. It would have changed the boundary, the top number. I mean, everything would have changed. So I don't want that to be a subtle assumption here. It's a very important assumption that we're starting with 1. Actually, sometimes we start with 0. So starting with 1 is not a flawless assumption. It could change. All right, so this one was very similar. Just recognizing the pattern. Notice it stopped at n, so there wasn't really anything we could calculate on that one. All right, so I said a moment ago that this is something we do because we like to expose a sum like this. And let me explain why by showing you this page.